Okay, this is Algebra 2 with trig, 7.4b. We're going to graph logarithmic functions. What we're first going to do is look at some review and how we write a logarithm in exponential form and how we write and evaluate the logarithm without a calculator. So take a few minutes with that, a few moments with that at least. Pause the video, come back and see how you did. All right, when we write this in exponential form, we like to say 5, we go around and we finish off with a little arrow that helps us remember that we're doing 5 to the third power equals 125. We have written the logarithm in exponential form. Here's a logarithm. It would be known as a common log, because it does not have a base that's written. When it doesn't have a base, that means that it's going to be a 10. It's a common log. So we're going to say 10 to the 5th power equals 100,000. And then to evaluate our logarithm without a calculator, if you need to convert it into exponential form, you could say equals x. You would go around and say 15 to some power equals 15. Well, because this 15 has an exponent of 1, the bases are the same, so x would have to be 1. And then for our last one, 3 to some power equals 1 over 27. We know that 27 is 3 to the 3rd power. To get it out of the denominator, we can say 3 to the negative 3rd power. The 3 cubed is 27. The negative puts it in the denominator. Now the bases are the same, so the x would have to be negative 3. Now we evaluated those all without our calculator. Okay, we're going to look at graphing logarithmic equations. The graph of a log is shown in 2 different situations where b is greater than 1. When the base is greater than 1, the logarithmic graph will be dropping down. Its inverse is exponential. We got 2 graphs here. We got one of the logarithmic, and we've got one of its reflection over y equals x. These 2 graphs are considered inverses, inverse functions. All right. The graph is a reflection over y equals x, just as we reflected equations in the past. Note that the y-axis, which is x equals 0, is a vertical asymptote. If you look here, going down for the logarithmic graph, there's your asymptote. What used to be the y-axis, or the x-axis as the asymptote, the exponential approached the x-axis. When we reflect it, we now approach the y-axis. What used to approach the x-axis, when we reflect it, it now approaches the y-axis. So if you ever wonder what's happening, you can look back at the exponential and see whereabouts it's heading to. The domain is going, the domain for a logarithm, here, the exponential, the domain was all real numbers. But if you look at our logarithmic graph, it doesn't go to the left of y equals, or the y-axis. So it's going to be x is greater than 0. That used to be the range. The range used to be y is greater than 0 for its inverse. But now when you do the inverse, the x is greater than 0. They switch, the x and the y switches. What used to be all real numbers for the x's is now all real numbers for the y's. So the range is all real numbers. So I'm trying to show you there that the domain and range of the exponential is now become the switch, the range and domain of the logarithm, logarithmic equation. All right, when we come down to graph, when we graph a logarithm, it's a little tricky to think about our table or where these points specifically go without thinking about the exponential that this would make. So a logarithm always equals an exponent. We know that. So 2 to the y power equals x. So instead of picking values for x, we're going to pick values for y. So we can do our calculation and find out what the best x is for that's going to be. So we can put in 0, we could put in 1, we could put in -1. You could really put in any numbers in there you wish, because for y, it's all real numbers. But we typically like to do it right around the x-axis. When y is 0, 2 to the 0 power, any number to the 0 power is always 1. So in our graph, when x is 1, y is 0. Now we have a y value of 1. We plug it into our exponential form. 2 to the first power is, of course, 2. So when x is 2, we're up at 1. And if you wanted to go further than that, you could talk about what happens when y is 2. Well, plug it into your exponential. When y is 2, you get 2 squared, which is 4. So when x is 4, you're up at 2. -1. When you have a negative exponent, that means take your base and put it into the denominator. So that's going to be 1/2. So when x is 1/2, you're down at 1. At -2, that would be 1/4. So when x is 1/4, we're down at -2, and so forth. We could talk about 1/8, 1/16. And we can see that the points keep getting closer to the y-axis, and they slowly keep growing. That's the equation y equals log base 2 of x. Okay, when we look here, we see that the graph is approaching the y-axis. We'll never get 0 for the x. We're getting closer. We got 4, 2, 1, then we got a half, a fourth. The next one would be an eighth, a 16th, 1 over 32, 1 over 64, 1 over 128. We're never going to get to 0. It'll only get closer to 0. So we have an asymptote right along the y-axis. X equals 0 is the asymptote. We connected all those points. We wrote our equation. We know that the domain is going from the y-axis and out. So wherever x is greater than 0. That's the domain. And the range goes down forever. And it does slowly but surely go up forever. You can look at the y values. You see that they go down. And you see that they go up. For our comparison, there is no comparison. There is no transformation. There's no stretching. There's no translating. There's no reflecting. All those would be possible with a logarithmic graph. The end behavior, this is a little funny. What does x approach as we look left? We often put down x approaches negative infinity. We say it goes to the left forever. But if you look here, it only goes to the left until we get to here. So this is approaching 0. So as x approaches 0, that's the furthest it can approach going to the left. It's never going to get to -1. It's never going to get to 0. What is happening to the y value as we approach that? As this y value, actually, as x gets smaller, what's the y value doing? It's going down also. It will go down to infinity. You plug in the right numbers, you'll get a y value of -10, -1,000. You can get any number for y. And as x moves to the right, it seems to move to the right pretty freely. No restrictions when x is moving to the right. So as that approaches infinity, the y value is also increasing to infinity.
Mr. Weber.
So now we're going to look at transformations. So you can graph equations in the format of our y equals log base b of x minus h, just like we have with all the other types of equations we've done. Plus k. By first graphing, we're going to graph y equals log base b of x. And then we're going to translate the graph horizontally, h units, and vertically, k units. Just as we have for all the different types of equations. The vertical asymptote will always be x equals h. So the asymptote is going to be whatever going up and down to the right, and that's determined by the h value. All right, so we'll try graphing this. Well, we're first going to graph y equals log base 3 of x. And to graph that, we're going to write it in exponential form. So we start with our base. We go to the exponent, which that's what a logarithm equals. And in exponential, we have it equal x. So we have log base 3 of x is part of our table. So we're doing a parent function for this. So we're going to pick y values of 0. Now we can pick any number we want to the right. You can pick 1, you can, oh, sorry. Don't we pick values for the y? We pick values for the y. It's just easier for your calculation. So we pick values for the y. You can pick 1 and -1. For the ones on the right and left, you could go 2 and -2. You pick any numbers, really. So when y is 0, when the exponent is 0, you know we're going to get the value of 1. So when x is 1, y is 0. When y is 1, we know the x value would have to be 3. 3 to the first power is 3. So when x is 3, y is 1. You can continue moving to the right if you want. You could do 2, and that would be 9. Well, that's going to take you out 1, 2, 3, 4, 5, 6, 7, 8, 9. That would take you way off the grid. 3 would take you out to 27. So far, we've come in and look like that. Looking to the left, when the exponent is negative, we take and put your base in the denominator. So we get 1/3. So when x is 1/3, we're down at -1. And we can continue that further if we wished. When x is -2, that would be 1/9. So that means when you're barely off the line, you're down by 2. And that's going to slowly but surely just keep getting closer and closer to that y-axis. So our y-axis is the asymptote. And that's x equals 0. Actually, you don't have to label that one. We typically just label the graph for the final one. I got carried away there, but that's fine. That equation is y equals log base 3 of x. So now when we do our transformation, only one that we have here is a translation. Transformation is all of the reflections, the stretches, and translations. The graphs that we do will only have translations to them. We won't reflect or stretch, but you still understand how that would all work. So we're going to translate 1 to the right and we're going to translate 2 up. So that's going to make our asymptote wherever the H value is. We can predict that right now, or we can graph it first. If we're going to graph it first, notice we're going to go to the right one. So we're over like 1/9. So we're 1 1/9. And we go up 2. Then we go over 1 and go up 2. We go over 1 and up 2. Over 1 and up 2. Over 1 and up 2. So our graph is now doing something like that. So our asymptote that we're actually interested in is x equals 1. We don't really care about that x equals 0. If you would want to erase that, you could do that. We really just want to know about x is 1, because x is 1 is the asymptote for the graph. The domain would have to be x is greater than 1, because we go from the 1 to the right is all the blue graph. The range goes up and down forever. We do have a comparison with this one. We're comparing it to the parent function. We translated 1 unit right, 2 units up. And our end behavior, we're going to be approaching the asymptote, and the asymptote is at 1. So now we're approaching 1. And as we do that, the y value, if you notice, the closer we get to 1, the y value gets lower. So the y value goes to negative infinity. And as we move the other direction, when x gets bigger, the y is slowly getting bigger. It will always get bigger. If you put in a bigger x, you'll get a bigger y.
Mr. Weber. Emily is in the waiting room again.
So here we have y equals log base 3 of x minus 1 plus 2. So we like to write our equation. So now you can go ahead and try the next 2 graphs. You can pause the video, work through it, come on back and see how you did. All right, to graph this one, we will first write it in exponential form. So we'll have 1/3 to the y power. Well, that's not where we write it. Way to go. We write 1/3 to the y power equals x. So in our table, we are graphing the log base 3 of x. So when the y value is 0, any exponent to the 0 power is 1. Down a little low. Sorry about that. For sure. Then when the function is 1, when y is 1, we see 1/3 to the first power. That gives us 1/3. We have -1. When the y value is -1, that flips your base over. So now you have a 3. So that is actually going to lay out our points in a different shape. We now have an x value of 3. and a y value of -1, an x value of 1 and 0, and 1/3 and 1. So now we're kind of coming in from the other direction. That's because our base is 1/3. It's less than 1. So we're going to come in this direction. So that's the y equals log base 1/3 of x. We know we have an asymptote at x equals 0. And we could say our domain, if we cared about that, we could say our domain was greater than 0 and our range was all real numbers. We have no comparison. And the end behavior, we're approaching 0, the graph is going up. We move to the right, the graph is going down. Further we go to the left, the higher the graph is going. The further we go to the right, the more the graph is going downwards. Okay, for our last one, we're first going to graph y equals log 1/2 to the x. And to do that, we're going to do the exponential of 1/2 to the y power equals x. So we plug in our 0, 1, and -1. You can make those 2 and -2 if you wish. We probably have some room for that. Anytime you have an exponent of 0, we get the answer of 1. That's the one point that seems to be pretty consistent with all of these. When our log base 1/2 of x, that's what we're values that we're working with. You plug in the 1 for the y, and x is going to be 1/2. Plug in a -1 for the y, and x is going to be 2. So you see that it's approaching infinity as we move to the left, and it's going to -infinity as we go to the right. Then we have our translation. We're going to take all of those points. We're going to translate 2 to the left, 1, 2, and 3 down. 1, 2, 3. 1, 2, 1, 2, 3. 1, 2, 1, 2, 3. When we do that, we have our asymptote that we're approaching. This is x equals -2. Our equation is y equals log base 1/2 of x plus 2 minus 3. And of course, our first one was log base 1/2 of x. In this case, of course, our domain would be x values being greater than -2, and a range being all real numbers. And as x approaches, let's see what x is approaching. As x gets smaller, it's only going to -2. So as x approaches that -2, the y value is going up. And as x gets bigger, the graph is going down. As x moves to the right, the graph is going down.